Electrical engineering exam questions. Hello everyone, welcome to my channel. My name is Rafael. I am an electrical engineer, linguist, and bilingual teacher of mathematics and physics from Brazil. And in this video, I would like to invite you to a debate about power in both direct current and alternating current circuits, and for this purpose I select several problems from the most important examinations for electrical engineers in Brazil. Let's begin with the first exercise. Exercise number 1 says, calculate the power factor of the circuit. This is the question. Let's go to the solution. Recall that above the capacitive reactance and the inductive reactance depend on the frequency of the source. As the frequency of the source increases, the inductive reactance increases, whereas the capacitive reactance decreases. The capacitive reactance can be represented as Xc is equal to 1 over Wc, and the inductive reactance is represented as Wl. In sinusoidal steady-state analysis, circuit elements are represented using complex impedances at a given frequency. The resistive impedance is represented by the resistance ZR is simply R. The capacitive impedance ZC is negative JXC, and the inductive impedance is ZL equal to JXL. The problem provided the impedances directly at a specific frequency. In this way, we know that ZR is equal to 10 ohms, ZC is equal to negative J 4 ohms, and the inductive impedance ZL is equal to J 14 ohms. Since the elements are connected in series, the total impedance is the algebraic sum. We simply sum then Z of the circuit is 10 minus J 4 plus J 14, which is equal to 10 plus J 10 ohms. Since the imaginary part of the complex impedance is greater than 0, it is inductive, which means that the current lags the voltage by the angle of the power factor. The magnitude of the complex impedance is, let's calculate the magnitude of the complex impedance. the magnitude of z is equal to the magnitude is the square root of r squared plus x squared, and this is equal to the square root of 10 squared plus 10 squared, which is 10 times the square root of 2 ohms. The power factor can be calculated in two ways. The first method, the power factor is the cosine of the angle in the impedance triangle. The first method, first, we draw the impedance triangle. The hypotenuse is the magnitude of the impedance. The lower side is the resistive part, 10, and the side opposite to the angle is the reactance, which is also 10. The power factor is the cosine of this angle here. 10 divided by 10 square root of 2, and this is equal to the square root of 2 divided by 2. This is the first method. Now let's go to the second method of calculating the power factor. Second method, the angle phi is also the phase angle between the voltage and the current, and can be calculated by, observe that phi is the inverse tangent of the reactance divided by the resistance, which is the inverse tangent of 10 divided by 10, which is 1, and the inverse tangent of 1 is 45 degrees. This angle represents the phase of the impedance, and therefore the phase difference between voltage and the current. Since the reactance is positive, the current lags the voltage by 45 degrees. Observe that the voltage phasor is here and the current here, and the angle is 45 degrees. The current lags the voltage by 45 degrees, and the power factor is, as we know, the power factor is the cosine of the angle, which is the square root of 2 divided by 2, which is approximately equal to 0.707, or if you prefer, 70.7%. What does it mean? It means that the power factor of 0.707 indicates that about 70.7% of the apparent power is converted into useful work. And this is all for the discussion of exercise number 1. Let's go to the next. Let's go to exercise number 2. Exercise number 2. For the circuit of the figure, resistor R2 dissipates 96 watts of power. In this way, what is the value of the current supplied by the source? This is the question. Let's go to the solution. To facilitate calculation and understanding, we will use two auxiliary currents, I1 and I2, and denote the voltage at the node as V1. We are going to consider the voltage here, V1. The current that flows here, we are going to call I1, and the current here will be I2. Applying KCL at the node will obtain. Remember that the sum of the currents that enter a node has to be equal to the sum of the currents that leave the node. In this way, I is equal to I1 plus I2. We can calculate I1 directly, but we cannot calculate I2 directly, as the values of R1, R2, and R3 are unknown. They cannot be used to determine I2. Instead, we use the voltage drop across R2 and the power it dissipates. Since R2 dissipates 96 watts and the voltage across it is 40 volts, observe that the voltage drop across R2 is 100 volts minus 60 volts equal to 40 volts. I2 can be obtained from P equal to V times I applied to R2. Thus, I2 is equal to 96 watts divided by 40 volts, which is 2.4 amps. We already know I2. Therefore, I, the current of the source, will be equal to I1. How can we write I1? It is the voltage of the node, 120 volts divided by the resistance, 200 ohms, plus I2, 2.4 amps. Now it is easy, simple mathematics. Dividing here, we find 0.6 amps plus 2.4 amps, which is precisely equal to 3 amps. And this is the current supplied by the source. And it is all for the debate of exercise number 2. Let's go to exercise number 3. Exercise number 3. What is the value of the total power dissipated in the circuit? This is the question. Let's go to the solution. To calculate the total power dissipated in the circuit, we may use the equivalent resistance. Observe that there is a delta in the circuit. In this configuration, we will not be able to find the equivalent resistance. Thus, it is necessary to convert the delta into AY. Remember that the impedance of the Y configuration is a third of the impedance of the delta configuration. In this way, Ry, the resistance of the Y configuration, will be a third of 6 ohms, which is 2 ohms. The delta is thus converted into AY. The delta six and 6 is converted into AY. 2, 2, and 2. And the circuit can be redrawn as, this is the new circuit, and in this new configuration we can calculate the equivalent resistance. And how can we calculate the equivalent resistance? Firstly, we observe that there are 2 series connections between a 2 ohms resistance and a 4 ohms resistance. Observe here the series combination between this 2 ohms resistance and this 4 ohms resistance, and the series combination between these 2 ohms resistance and that 4 ohms resistance. In this way, equivalent resistance number 1 is equal to 2 ohms plus 4 ohms, which is equal to 6 ohms. And likewise, equivalent resistance number 2 is 2 ohms plus 4 ohms, which is equal to 6 ohms. Next, we observe that there are 2 6 ohms resistances in parallel. Equivalent resistance number 3 is the parallel combination between 2 6 ohms resistances, and the rule of thumb that we use in computing the parallel combination between 2 resistances in parallel is the product over the sum. That is 6 lots of 6 divided by 6 plus 6, which is equal to 3 ohms. Now there are 2 resistances in series, this and this. The total equivalent resistance is 2 ohms plus 3 ohms, 5 ohms. With the value of the equivalent resistance, we can calculate the total power dissipated in the circuit using this expression. The total power is equal to V squared divided by the total equivalent resistance. The voltage is 10 volts. And the total equivalent resistance is 5. And this is equal to 20 watts. And this is precisely what the exercise wanted us to calculate. And it is all for the discussion of exercise number 3. Let's go to the next. Exercise number 4. Determine the reactive power and the active power demanded by the circuit. This is the question. Let's go to the solution. We can solve this question using 2 methods. The first method consists of determining the active power and the reactive power using the complex power. The first method, if we establish that the voltage of the source is 100 phase 0 degrees, we can calculate the current. The current is simply the division between the voltage and the sum of the impedances. And this is equal to 2 phase negative 53.13 degrees amps. This is the current. With the voltage and the current, we can calculate the complex power. Observe that these are phasors. This is the current phasor and this is the voltage phasor. The complex power is the magnitude of the complex power is the apparent power in a phase, which is equal to the multiplication between the voltage phasor and the complex conjugate of the current, that is S is equal to 100 phase 0 degrees volts multiplying the current to phase positive 53.13 degrees amps. Observe that this is the complex conjugate, so we invert the sign of the angle of the current phasor. And this is equal to 200 phase 53.13 degrees volt-ampere. This is the complex power. We calculated the complex power, and with the complex power we can calculate the active power and the reactive power. P is equal to S, the apparent power, which is the magnitude of the complex power, times the cosine of the angle, that is 200 times the cosine of 53.13 degrees, and this is equal to 120 watts. This is the real or active power. Likewise, we can calculate the reactive power. The reactive power, Q, is equal to the apparent power times the sine of the angle, 200 times the sine of 53.13 degrees, and this is equal to 160 VAR. This is the first method of solving this question using the complex power. Let's see now the second method. The second method consists of determining the real power and the reactive power using the complex impedance. We know that the complex impedance is Z equal to 30 plus J 40 ohms. The magnitude of the complex impedance is therefore the square root of 30 squared plus 40 squared, and this is equal to 50 ohms. The magnitude of the current can be calculated using the magnitude of the voltage and the impedance. The magnitude of the current is equal to the magnitude of the voltage divided by the magnitude of the impedance, and this is equal to 100 divided by 50, and this is equal to 2 amps. This is the magnitude of the current. With the magnitude of the current, we can calculate the powers. P is equal to R times I squared, and this is equal to 30 ohms times 2 amps squared, and this is equal to 120 watts. Likewise, we can calculate Q. Q is equal to X times the magnitude of the current squared, that is 40 times 2 amps squared, and this is equal to 160 VAR. And this is the solution of exercise number 4. And it is all for the discussion of this exercise. Let's go to the next. Exercise number 5. Determine the load power factor given that the instrument readings are 100 volts, 20 amps, and 1760 watts. This is the question. Let's go to the solution. Observe that this is an extremely simple exercise. It requires only the use of the following expression. P is equal to V times I times the cosine of the angle. And the cosine of the angle is exactly what we want. We want the power factor of the load, which is equal to the cosine of the angle. And we can calculate using the values that the exercise provided. 1760 divided by 100 volts times 20 amps, and this is equal to the power factor is equal to 0.88. Thus, the load power factor is 0.88, and it is precisely what the exercise requested from us. And it is all for the discussion of this exercise. Let's go to the next. Exercise number 6. Consider a load supplied at 220 volts, drawing 10 amps with a 90% power factor. Determine its apparent power and active power. This is the question. Let's go to the solution. Observe that the apparent power is the magnitude of the complex power. The complex power is represented as and can be calculated by multiplying the voltage phasor with the complex conjugate of the current phasor. And the apparent power is found by multiplying the magnitudes of these phasors. In this case, 220 volts times 10 amps, and this is equal to 2.2 kVA. This is the apparent power. To calculate the real power, we use the power factor. The exercise provided the power factor. P is equal to S times the power factor, that is 2.2 kVA times 0.9. And this is equal to 1.98 kilowatts. And this is all the exercise requested from us. The apparent power and the real or active power. And this is all for the debate of exercise number 6. Let's go to the next. Exercise number 7. What is the power factor of the load shown in the figure? This is the question. Let's go to the solution. Remember that the power factor is the cosine of the phasor angle between the voltage phasor and the current phasor. Therefore, the phasor angle phi is equal to negative 20 degrees minus positive 40 degrees, which is equal to negative 60 degrees. With the phasor angle, we can calculate the power factor. The power factor is equal to the cosine of the angle. In this case, it is the cosine of negative 60 degrees, which is equal to 0.5. In addition, observe that as the phasor angle is negative, the power factor is capacitive, which means that the current leads the voltage by 60 degrees. The current, observe here, the current leads the voltage by 60 degrees. And this is all for the discussion of this exercise. Let's go to the next. Exercise number 8. An electrical installation has 8 kilowatts of active power and 10 kVA of apparent power. Determine the reactive power of the installation. This is the question. Let's go to the solution. Observe that regardless of whether the installation is single phase or three phase, the following relationship holds. S squared is equal to P squared plus Q squared. Observe the power triangle. We can easily calculate the reactive power. Q is equal to the square root of S squared minus P squared. In this case, it is the square root of 10 squared minus 8 squared, and this is equal to 6 kVAr. Thus, the reactive power of this installation is 6 kVAr. This is a very simple exercise just to train working with the power triangle. And this is all for this exercise. Let's go to the next. Exercise number 9. What is the power factor of the circuit of the figure? This is the question. Let's go to the solution. Note that the complex impedance of the circuit Z is equal to R plus JXL. R is 21 and XL is 28. This is the complex impedance of the circuit. The power factor is the cosine of the angle of the impedance. Observe the impedance triangle. The power factor is the cosine of this angle here. The power factor is the cosine of that angle, which is equal to R divided by the magnitude of Z, We know R, but we don't know the magnitude of Z. Let's calculate the magnitude of Z. The magnitude of Z is equal to the square root of R squared plus XL squared. In this case, it will be the square root of 21 squared plus 28 squared, which is 35. The power factor is therefore, the power factor is 21 divided by 35. And this is equal to 0.6. That is, by definition, the cosine of an angle is the adjacent side divided by the hypotenuse. The adjacent side is R, 21, and the hypotenuse is the magnitude of the complex impedance. We calculated and we found 35. But there is an alternative method. The alternative method consists of converting Z from its Cartesian form, 21 plus J, 28, into its polar form, which is 35 phase 53.1 degrees. The power factor is the cosine of the angle of the complex impedance in its polar form. The power factor is the cosine of 53.1 degrees, which is equal to 0.6. The direct conversion from the Cartesian form to the polar form can only be made through the use of a calculator. If you cannot use a calculator in an exam, then you're gonna need to remember the first method to solve, which consists of simply dividing the resistance by the magnitude of the complex impedance. And this is all for exercise number 9. Let's go to the next. Let's go to exercise number 10. Exercise number 10. The instantaneous power of a load is given by P of t is equal to 10 plus 10 times the sine of 377t plus 10 degrees watts. Calculate the minimum, the maximum, and the average power in watts. That's the question. Let's go to the solution. Observe that the instantaneous power depends on the value of the sine function, which varies between -1 and 1. Therefore, the minimum value will be P. Minimum is equal to 10 plus 10 times -1, which is equal to 0 watts. The average value will be P average is equal to 10 plus 10 times 0, which is equal to 10 watts. And the maximum value is P max is equal to 10 plus 10 times 1, which is equal to 20 watts. This is a very simple exercise just to debate the minimum, the average, and the maximum values of the instantaneous power. And this is all for exercise number 10. Let's go to the next. Exercise number 11. Consider the following circuit. What is the power dissipated in the 100 ohms resistance? This is the question. Let's go to the solution. The power dissipated in the resistor can be easily found using this expression. P is equal to V squared divided by R. Simply, we know the value of V and the value of R. We simply use the values provided by the exercise. It is 10 volts squared divided by 100 ohms. And this is equal to 1 watt. Very simple exercise. You just need to remember this expression to calculate what the exercise wanted you to calculate. And this is all for exercise 11. Let's go to the next. Exercise number 12. What is the value of the power supplied by the voltage source of the circuit? That's the question. Let's go to the solution. Among other possibilities, we can find the value of the power using the equivalent resistance. Firstly, we compute the series combination between the 7 ohms resistor and the 5 ohms resistor at the right. At the right of this circuit, there is the series combination between a 7 ohms resistor and a 5 ohms resistor. This combination will be equivalent resistance number 1. Equivalent resistance number 1 is equal to 7 ohms plus 5 ohms, which is equal to 12 ohms. Subsequently, we calculate the equivalent resistance resulting from the parallel combination between two 12 ohms resistances and one 6 ohms resistance. These two in parallel with this. And how can we calculate the parallel combination between three resistances? It is 1 over equivalent resistance number is equal to 1 over 12 plus 1 over 12 plus 1 over 6. It is easy to calculate. The lowest common denominator here is 12. 12 divided by 12 is 1. 12 divided by 12 is 1. 12 divided by 6 is 2. One over equivalent resistance number 2 is equal to 4 divided by 12. And we find that equivalent resistance number 2 is 3 ohms. To finish, we calculate the equivalent resistance between a 3 ohms resistance in series with a 7 ohms resistance. This will be in series with this, and the total equivalent resistance is 3 plus 7, which is equal to 10. The total power supplied by the source is equal to the power consumed by the equivalent resistance. We use this expression, P is equal to V squared divided by R, which is 60 volts squared divided by 10 ohms, and this is equal to 360 watts. And this is what the exercise requested from us. The value of the power supplied by the source, which is equal to the power consumed by the total equivalent resistance. And this is all for exercise number 12. Let's go to the next. Let's go to exercise 13. Exercise 13, determine the value of R for maximum power transfer. This is the question. Let's go to the solution. The exercise requested from us the value of R for maximum power transfer, and in purely resistive circuits, for maximum power to occur, R must be equal to the equivalent resistance of the circuit. To calculate the equivalent resistance of the circuit, we open the circuit at the load and we set the voltage source to 0. We open the circuit at the load and we set the voltage source to 0. And a voltage source set to 0 is a short circuit. After doing this, we reach this circuit here. However, observe that this circuit is harder for us to observe what's happening. Then it is better to remodel the circuit into this configuration for better visualization. Observe that the equivalent resistance is the parallel combination between two 16 ohms resistances and the parallel combination between a 20 ohms resistance and a 5 ohms resistance. Thus, the equivalent resistance is the parallel combination between two 16 ohms resistances and the parallel combination between a 20 ohms resistance and a 5 ohms resistance. And the rule of thumb that we use in computing the parallel combination of two resistances is the product over the sum. Thus, it will be 16 lots of 16 divided by 16 plus 16 plus 20 lots of 5 divided by 20 plus 5. And this, if you calculate, you're going to find 12 ohms. Therefore, the value of R that enables maximum power transfer is 12 ohms. Very simple, isn't it? And this is all for the debate of exercise 13. Let's go to the last. Let's go to exercise 14. Let's go to the last exercise. Let's go to exercise 14. What is the value of the load resistance that, if connected to terminals X and Y, ensures maximum power transfer? The exercise provided this circuit and requested from us the value of the load resistance that, if connected to terminals X and Y, ensures maximum power transfer. This is the question. Let's go to the solution. For a purely resistive circuit, the load resistance that enables maximum power transfer must be equal to the equivalent resistance seen from the load terminals. To calculate the equivalent resistance, the sources must be set to 0. A voltage source becomes a short circuit, whilst a current source becomes an open circuit. The voltage source will become a short circuit and the current sources will become open circuits. Let's calculate the equivalent resistance. Observe that at the left there are two 4 ohms resistances in parallel. And how do we know that they are connected in parallel? Because they share 2 terminals. This is common to this and this is common to this. Thus, equivalent resistance number 1 is 4 in parallel with 4, and the rule of thumb that we use in computing the parallel combination between 2 resistances is the product over the sum. 4 lots of 4 divided by 4 plus 4, which is equal to 2 ohms. These 2 ohms resistance will be in series with the 2 ohms resistance at the bottom of the circuit. This will be in series with this. Thus, equivalent resistance number 2 is equal to 2 ohms plus 2 ohms, which is 4 ohms. These 4 ohms will be in parallel with these 4 ohms. And as we know, equivalent resistance number 3 is 4 ohms in parallel with 4 ohms, which is 2 ohms. We already calculated this. This 2 ohms resistance will be in series with the 8 ohms resistance at the top. This will be in series with this. Thus, equivalent resistance number 4 is equal to 2 ohms plus 8 ohms, which is 10 ohms. Finally, this 10 ohms resistance will be in parallel with the 10 ohms resistance at the right. This will be in parallel with this. The total equivalent resistance is the parallel combination between 10 ohms and 10 ohms, which is 10 lots of 10 divided by 10 plus 10, which is equal to 5 ohms. As we already understood, for maximum power transfer, the load resistance must be equal to the equivalent resistance of the circuit. Load has to be equal to 5 ohms. And this is all for the discussion of exercise 14. And this is all for this video, my friends. I hope you enjoyed it and learned from it. I am a teacher, guys. If you want to book a lesson with me, use my WhatsApp number. Goodbye!